average geological year, there were major earthquakes in Guatemala, in China, and in the Philippines. There was a violent volcanic explosion in Guadeloupe. All geological events which were major items in the newspapers. If you were to drive along the road along the foot of the Niagara Escarpment, you'd be driving over the deposits of a sea about 400 million years old. If you were to drive along Highway 11 to the north, or Highway 69, you'd be driving through the roots of a mountain chain. And I could go on and I could list other examples of the way that geology surrounds us all, either in the form of rock cuts or items in the newspaper. The aim of the 22 programs in this series is to share with you the understanding that geologists have of geological phenomena and the geology that is around us. We have not fought shy of the difficult areas of geology and the jargon-laden areas of geology, but we have tried to keep the programs as lucid as possible, so those of you without a scientific background can follow the programs. But I should remind you that as well as watching the programs, we hope that you will be reading the material that we have either recommended to you if you're just a general viewer, or have made compulsory if you're a partaker of the course of which these programs are a part. The mineral and the rock kits are an important part of the auxiliary material. If you don't have these yet, you can get information on how to get them by writing to OECA. The first program of the 22 deals with the concept of geological time, and the first half hour of the hour is one of the Planet of Man films, The Voices of Time. It makes something of an emotional appeal to your understanding of geological time. In the second half hour, we'll go into a rather more geological interpretation of how geologists record or read the time recorded in rocks.
We decided to make this series for two reasons. One is that the mineral industry is a very important one in Canada, and indeed everywhere in the world. The other thing is that there has been a very exciting revolution in the earth sciences. We used to think of the Earth as being a fixed, static body with the continents permanently in position. We now know that they're moving around very slowly, and this has profoundly altered all our ideas about the Earth. So I hope that this series will cover some of the key ideas in geology today and show what opportunities there are, what excitement there is, and what interest there is in the Earth. It's almost impossible to imagine the full length of geologic time. Take these rocks around us here. They were probably formed in the heart of mountains 1,000 million years ago. And these mountains must have towered thousands of feet above where we are. And all that has been eroded away by the slow processes of rain falling, of frost, of glaciers, of stones rolling down hills, being carried away by streams. It's impossible, I think, to comprehend the vastness of that period of time, 1,000 million years. And yet it's only a quarter of the history of the whole Earth.
Compress the 4.5 billion years of geologic time into one calendar year. On such a scale, the oldest rocks we know date from about mid-March. Living things first appear in the sea in May. Land plants and animals emerge in late November. Dinosaurs become dominant in mid-December, only to disappear a week later. Man-like creatures appear sometime during the evening of December the 31st. Rome rules the Western world for 5 seconds, from 11:59:45 to 11:59:50 on New Year's Eve. Columbus discovers America 3 seconds before midnight, and the science of geology is born about 1 second before the end of this eventful year. In fathomless space, all things are relative. To the small, a microsecond may span an eternity. To the large, 1,000 years may pass in the wink of an eye. To a giant passing through them, the countless galaxies, and within each the still more countless stars and planets, might seem no more than motes of luminous dust, like fireflies whirling aimlessly in a dark night. Our giant might grant this cloud of 100 million stars, the Milky Way, no more than a cursory glance, and pass it by, unaware of the microscopic intelligent life that thrives here. One of 100 million, the planet Earth. It has existed long enough to revolve about its own sun approximately 4.5 billion times. But the presence of intelligent life here is a much more recent phenomenon. In the history of the Earth, man is but an upstart, the most recent syllable in an immense tale. He measures the brief story of his kind in hours and days and weeks and years. Measures it carefully to the frontier of his beginnings. If he wishes to go further, he must confront a space so vast that even the greatest of his yardsticks for measuring time is too minute, too inadequate for the task. In that immense space that man calls prehistory, years are measured in the millions, and time is calibrated by changes of the earth itself.
Time for rivers to wear away the land.
Time for generations of beasts to thrive and vanish from the earth.
Time for deserts to become oceans and deserts once again.
Time for mountains to rise and decay once more into plains.
Time for the earth to change its face 1,000 times.
The Grand Canyon, an unimaginative name for a unique experience. For here, visible to the trained eye, one half of the story of the earth lies exposed. A story told in rock that begins over 2 billion years ago. The story begins with water, wind, and fire. Agents that in time deposited layer upon layer of sediments and lavas in a sterile sea.
"2 billion years ago, The earth trembles, cracks, and heaves.
A day becomes a week, becomes a month, becomes a year, becomes a century. 1,000 centuries becomes a million. A million, tens of millions.
Now, a range of mountains towers where a plain once stood.
In the process of mountain building, immense pressures and heat altered the sedimentary rock and contorted the layers. In the inner gorge, only the roots of those ancient mountains remain. The walls of contorted rock reveal how molten material from deep within the earth forced its way into the base of the newly created mountains to cool, to harden, to seams and masses of pink crystalline granite.
Time passes.
The slow, inevitable action of wind and rain, heat and cold, washes the mountains away.
Time passes.
And the plain becomes a sea.
Those long vanished waters have left their mark, a signature written in sandstone layers, the sands of ancient beaches. In brilliant red shales, the hardened muds of river deltas. And in these rock layers, the first trace of life itself. Peculiar structural patterns etched in limestone, the mark of ancient reefs built up by the activity of minute primitive plants. These algae thrived in the warm tidal waters that were here over 600 million years ago.
Time passes.
And the seas withdraw, leaving an arid plain.
Time passes.
And the land shakes, and a second mountain range is built upon the roots of the first. And in their time, these mountains too erode away.
Another surf rolled in upon the land. Gradually, the sand deposited near the shore was covered by mud, and this, in turn, by lime, as the seas continued to deepen. These thick horizontal bands of rock bring another message from the world past. In the rich medium of the seas, life was evolving, becoming larger, more complex. The belligerent, the benign. The protected, the vulnerable. And the new rulers of the brave new world, the trilobites. Growing to 10 inches or more in length, they were the largest creatures in existence.
Time passes.
And the first fish appears in the seas.
Time passes.
And the land rises above the sea, and scorpions and millipedes become the first air breathers.
Time passes.
And the surface of the land is worn and washed away.
Rivers scoured channels as they meandered across long, vanished plains. Lavender-colored muds settled into these river scars, carrying with them evidence of a new era, the age of fish. Bulky, primitive creatures encased in bony armor, they left a record of their passing in skeletons, scales, and plates.
Time passes.
And the seas invade again.
A wide and quiet sea. In shallow water, marine animals, often called sea lilies, thrived. Their jointed arms waved to and fro, gathering food. In deeper water, countless millions of tiny plant and animal skeletons rained down to the bottom of that ancient sea. Too small to be seen with the naked eye, their structure only becomes apparent when magnified thousands of times. For every 1,000 years, an inch of sediment, a half inch of rock. 30 million years of skeletons leaves one of the most prominent and conspicuous features in the Grand Canyon, vertical cliffs of limestone over 500 feet thick.
Time passes.
And the seas give way to sediments washed down from distant mountains.
300 million years ago, the seas had a tug of war with the land. Layers of red sandstone deposited by freshwater rivers alternate with shales rich in seashells. The sandstone forms ledges. The softer shales form slopes. Finally vanquished, the sea retreated, leaving behind a reddish-brown arid land. During wetter periods, plants thrive on the lush flood plains. Ferns and other spore-bearing plants grew into forests that sheltered four-footed animals. These reptiles had but one skeleton to leave behind, but in the muddy banks of streams they left myriad traces of their passing. Covered by sand, cemented by waterborne minerals, they hardened to stone. The deep impressions and shortness of stride suggest heavy-bodied animals with short legs, probably more at home in water than on land.
Time passes.
The earth changes.
Time passes.
More life evolves.
The climate of the region became progressively hotter, more arid. The water evaporated from the land, leaving a cracked and parched earth. Memories of another time are preserved here in the ripple marks of vanished streams and the molds of salt crystals.
Time passes.
And a flood plain becomes a desert.
Arid, barren, the realm alone of the lizard and the scorpion, this age too is preserved in the walls of the canyon. Layers of cross-bedding, created as the wind-blown sand accumulated in dunes. And the tracks of a scorpion that passed this way 250 million years ago.
desert becomes a sea.
The seas that advanced and inundated the desert were warm and shallow. They deposited layers of limestone and sandstones. Time has weathered these sediments to peaks and pinnacles. Fossilized in them is abundant evidence of the new forms burgeoning beneath the seas. Mollusks, corals, sponges, sea lilies, and the tooth of a shark that cruised these waters some 200 million years ago.
And the seas withdraw once more, exposing the land.
In the period following the retreat of the seas, life flourished. Great evergreen trees grew to heights of 200 feet, and animals were growing to unprecedented sizes. An early ancestor of the crocodile, the phytosaur, left his bones in the accumulating muds to be unearthed again with the passage of time. In the petrified forest are some of the remains of those great evergreen forests. Now incongruously stranded in sand and exposed by erosion, they were carried here, floated along by turbulent rivers until they came to rest. A 200-million-year-old log jam. Over many years, these logs began to decay, but as they did so, mineral silica in the water replaced the decaying wood, part for part, preserving a replica in stone. In some cases, the water that seeped into them carried iron and manganese to stain the original into a brilliant array of colors.
Life evolves. And generations of great creatures walk upon the land.
About 160 million years ago, the world saw some of the largest creatures ever to walk the earth. The age of the dinosaur had begun. These huge lizard-like animals are indeed well named, for dinosaur means terrible lizard. They enjoyed a tenure here that was proportionate to their bulk. For nearly 150 million years, they ruled unchallenged. Some armored like tanks, were gentle herbivores, browsers of soft plants and grasses. Others, equipped with razor-sharp teeth and claws, were savage carnivores. These huge creatures had surprisingly small brain cavities and very little, if any, intelligence. Whether it was a climatic change or something as simple as a primitive mammal with a taste for their eggs has never been determined, but these immense creatures filed out of history and into extinction as surely as all that preceded them.
Time passes.
And a river wears away at the land.
Over the next 100 million years, through the age of the mammals and the long prelude leading to the evolution of man, a river flowed persistently across the Grand Canyon area. As the plateau began to rise stubbornly, almost imperceptibly, the river chewed away at 2 billion years of accumulated deposits. In the lands beyond the canyon, these centuries saw the passing of 4 great ice ages. And the slow evolution from ape to man. As past moved into present, the river wore ever deeper, exposing 1/2 of the history of the Earth. And the rains carved the peaks above it. Finally, only 3,500 years ago, the first traces of a new species of animal appeared on the Grand Canyon Plateau. It was the first announcement here of the advent of another age.
A new generation of creatures thrives upon the land.
To date, theirs remains the briefest tale of all.
If you look back over the program you've just seen, The Voices of Time, I think you'll find yourself impressed by two things. First of all, the immensity of geological time. The Grand Canyon alone preserves a record of the last 2 billion years, and even that's less than half of the age of the Earth. And the second thing that I think that you'll find yourself impressed with is the way that geologists can take rocks like those in the Grand Canyon and interpret the geological history of the area from them. And by geological history, I mean the comings and goings of seas and the building and the wearing down of mountain ranges. It sounds a formidable task, but it's not so very difficult. And if we look at some of the rocks that one might find in an area like the Grand Canyon, I think perhaps that you'll agree. These are rocks like those found in the Grand Canyon. And there's a very obvious, visible difference. This rock is a platy one, rather like a paving stone. It's formed of sand and mud, and on its surface, it has the trademarks of a rock which was deposited in water. These little ripple marks must be familiar to anybody who's ever walked along the shore of a lake or a beach. This second rock has not got such clear layering in it, but it has some layering. This dark band is quite clearly distinct from the pinkish bands in this rock. This is a metamorphic rock, and the clues that it yields to the history of an area lie in the fact that to produce this kind of rock, sedimentary rocks must be cooked and put under pressure equivalent to several miles of overlying rocks. So metamorphic rocks occur in the roots of mountain bolts, and when we see them at the surface, we know there was a mountain bolt once there. This rock is distinct yet again. It has no layering at all, and if you were to take a hand lens, you would see that it was composed of interlocking crystals. That rock is an igneous rock. It was once molten. It's the kind of rock that we get when lava crystallizes. If you can recognize the differences between those rocks, then you can interpret road cuts. A road cut like this one, for example, is formed of sedimentary rock. It was taken close to the university in Sudbury. This one here was taken down Highway 69. It's clearly of a metamorphic rock. And if you can recognize it, then you can tell that in this area there was once a mountain range, and you're looking at the eroded roots of that mountain range. Now, you can do that anywhere, and there's some books which will help you. There's a series of books produced by the Geological Survey of Canada, one for each of the national parks, right from the west, from the Rocky Mountains, through to Prince Edward Island in the east. There are also books produced by the Ontario Department of Mines. There are a number of these, 4 at present, and they describe the geology of various parts of Ontario. Geology is, in fact, very much a science in which everybody can make their own observations and interpretations. All you need to be able to do are basically to recognize those 3 kinds of rocks that we talked of and know how to interpret them. And this course is designed to give you the background to do just that, and the background to be able to look at the way that the Earth works and to be able to understand the way that the Earth works. There are 22 hours of television, 16 specially produced hours, and 6 hours of OECA's Planet of Man programs. But it's important that you remember that the main part of the material that's needed to begin learning about geology is contained in the textbooks that we've recommended to those of you taking the course, and in the notes that we've supplied you with. The television programs cover most of the topics of geology, but they don't cover everything. The programs are of various kinds. There are programs which cover the ground rules which geologists use in looking at the Earth as a whole. And surprisingly enough, even though geology is 200 years old as a science, those ground rules have changed relatively recently. In the last 10 years or so, it's become clear that the Earth is covered by a shell of rigid, rocky plates, which fit together rather like the pieces of a spherical jigsaw puzzle. This picture of the Earth has revolutionized the way that geologists look at our planet, and it's also fundamental to this course. We'll be concerned with plates, for example, in the unit which deals with volcanoes, because active volcanoes are generally located at the margins of the plates. Earthquakes are also located at the margins of plates, and earthquakes will be the subject of another unit in the course. When plates converge, oceans are squeezed out of existence, and mountains are built when continents collide. This dramatic animation is from one of the best of the OECA films. Mountain building and the geological character of oceans are the subjects of their own units in the course. New mountains, like the Himalayas, born through one geological process, are subjected to simultaneous destruction by another, erosion. And we shall also examine erosion in one of the later units in the course. These worn-down mountains are the Appalachians, formed about 300 million years ago when Europe, North America, and then Africa collided. The Appalachians are the topic of the OECA film included in the unit on mountain building. As well as looking at the ground rules for global geology in some of the early programs, we'll also take a look at the real stuff of geology, at minerals, and we won't forget the way that minerals are put together at their atomic structures, and also at rocks, not just trying to pigeonhole rocks, trying to distinguish them one from another, but looking at the way that they originate. For example, this sedimentary rock with its ripple marks. And we'll find that those units, those early ones, are some of the most difficult in the course, in fact. This beach sand bears a very easily readable clue to its origin, and much of the study of sedimentary rocks involves making comparisons between the present and the past, between today's processes and yesterday's rock. Lab experiments are also important in understanding rocks, and we've included in the TV programs film of many laboratory demonstrations. This one shows how grains are cemented together when sandstone forms from loose sand. And this one shows a hot liquid crystallizing, an important process to understand when interpreting igneous rocks, those which crystallize from a molten liquid, for example, lava. One experiment commonly used by geologists in this field is the simulation of the conditions under which molten material crystallizes at great depths far beneath the surface of the Earth. Rock powder is heated to melting point and then allowed to cool under great pressure. Comparison of the composition and structure with an actual rock reveals whether the geologist's estimate of the temperature and pressure was accurate or not. Many rocks show clear evidence of having been deformed, bent and folded in a manner which seems quite impossible for rock. But silicone putty, an everyday substance which shatters under a hammer blow, but flows under pressure applied slowly over a period of time, shows us that we shouldn't take familiar substances for granted. By the time you get halfway through the course, the way that rocks form and what makes them up and the way that they behave under increased temperature and pressure should be old hat to you. And it's at this stage that we'll start looking outside our own planet at the other planets, because nobody who studies the Earth can really be satisfied without knowing how the Earth compares with the other planets. We shall look at the origin of the solar system and at the similarities and differences between the planets in the light of the results of the space program of the last 15 years.
I was strolling on the moon one day in the merry, merry month of December. Now, May.
The moon, because of the dramatic success of the manned Apollo flights, gets a program of its own.
We'd like to dedicate the first steps of Apollo 17 to all those who made it possible.
Geology is a very broad subject. It overlaps into chemistry and the study of minerals and of rocks, and into astronomy when we compare the Earth with the other planets in our solar system. It also overlaps into biology, because rocks don't only reveal the conditions under which they originated, but they also contain the remnants of the history of life. They contain fossils. We'll devote 3 units of the course to examining the fossil record, the origin and the evolution of life, beginning once again in the laboratory. Experiments such as this one, carried out in the early 1950s, have shown that it was possible for important organic molecules, such as amino acids, to have developed on Earth from the inorganic ingredients we might expect to have existed in the early seas. Lightning strikes may have provided the energy simulated by the experimenter's spark, but the results of that experiment are still very, very far from explaining the development of the complex biological processes which have governed life and evolution over the last few 100 million years. There are still large gaps in our knowledge in this area. However, we do know that it was primitive plants giving off tiny bubbles of oxygen which changed the atmosphere of our planet and paved the way for the evolution of higher animals, including ourselves. Although geology is basically an historical science, it's also a very practical one. Canada, without its geologists, would quickly become very poor. And this is because it's geologists that find this stuff. This is copper ore from Sudbury, and we need a lot more of it. Last year, Canada's mineral industry contributed $15 billion to Canada's economy. And in coming years, minerals and finding them is going to become even more important. We have a couple of units which deal with the techniques of finding mineral deposits and also deposits of fuel, oil. Our main concern in the 2 units which cover ore deposits will be to look at the processes by which the ore originates. One of the world's most valuable and renowned mineral deposits occurs on the doorstep of Laurentian University here in Sudbury. Discussing the geology of this deposit will involve us in considering the possibility that the ore originated as a result of a meteorite impact about 2 billion years ago. Mining has been going on in Sudbury since the beginning of the century, and the deposit is so large it will undoubtedly continue for many years yet. In the same program as that in which we look at the Sudbury deposit, we'll try to cover the geology of what many people have suggested is one of Canada's most troublesome riches, the Athabasca tar sands. These tar sands are the world's richest deposit of liquid hydrocarbon. Current technology can recover about 1 million barrels of oil a day for the next 750 years. Although the exploitation of such deposits depends upon technology and machinery and on politics, geological mapping and surveying is at the root of this discovery, as it's at the root of almost all economic discoveries. The Geological Survey of Canada had thoroughly investigated the tar sands as early as 1888. Like all other natural hydrocarbons, the tar sand originated from tiny marine organisms which died in the seas which flooded Alberta probably about 300 million years ago. But the economic aspects of geology are not the main aspects on which we want to concentrate in this course. By the end of the course, we want you to have an understanding of how the Earth works. And not only do we want you to have an understanding of how it works, but also we want you to have the vocabulary that's necessary in order to discuss and communicate your understanding. It's no good, for example, if we go back to the Grand Canyon, each time you want to refer to this sandstone, having to say the sandstone that's 800 feet above the base of the Grand Canyon at Zuni Point. That's an awfully long-winded way to talk about that sandstone. You need to develop the kind of vocabulary that will enable you to talk about that sandstone to another geologist in a meaningful way. And the vocabulary that geologists have devised is the geological time scale. Like prehistorians, geologists have divided geological time into what we call periods. The prehistorians use Stone Age and Iron Age and Bronze Age. Geologists use Cambrian, Ordovician, Silurian, Devonian, Mississippian, and so on. The major part of the geological time scale, however, is the so-called Precambrian, and that is the bundle of rocks that are older than 600 million years old, which contain very few fossils. Because the trademarks that geologists use in order to recognize the rocks which belong to the geological periods are fossils, in the same way as the prehistorian uses artifacts in the rubble on the floor of a cave in order to identify when the cave was inhabited. Geologists use fossils in order to identify the period to which the rocks that they're looking at belong. So a geologist in the Grand Canyon then would be able to refer to this sandstone as the Cambrian sandstone in the Grand Canyon. He wouldn't say the sandstone 800 feet above the base of the canyon. So let's put in the periods to which the geological strata of the Grand Canyon belong. Cambrian strata at this point. And everything beneath that is Precambrian and contains no important fossils. Above the Cambrian, the next strata that we encounter are Devonian rocks, representing deposition of sediments during the passage of Devonian time. And the next, Mississippian strata. The passage of Mississippian time is represented by this limestone, this thick cliff of limestone. And Pennsylvanian time is represented in the canyon by these strata. And finally, at the top of the canyon are Permian strata. Now then, if you go back and you look at the geological time scale in your text, or you've already remembered and learned it, you'll see that there's a gap. There's a gap between the Cambrian and the Devonian. There are no representatives in the canyon of Ordovician and Silurian strata. Now then, that's what we call an unconformity. We say there's an unconformity between Cambrian strata and Devonian strata in the Grand Canyon. What does it mean? Well, what do those strata represent? They represent the deposits of successive seas. And if there are no deposits, there was no sea. And therefore, in the Grand Canyon, we know, because there's an unconformity between the Cambrian and the Devonian, that in Ordovician and Silurian time, the Grand Canyon was a land surface and was not covered by sea. We can spot unconformities in the Grand Canyon at this level also, beneath the Cambrian. This is another land surface in the Grand Canyon. And we can spot it because these strata of the Precambrian are tilted, and the strata of the Cambrian are horizontal. This level was a land surface about 600 million years ago and was flooded by Cambrian sea, which deposited this sandstone. And that sandstone is the record of Cambrian time, just in the same way as snow is a record of a snowstorm in winter. The snow melts away, but the sands and muds don't. The sand and mud remain as a permanent record of that time. The unconformity between the Cambrian and the Devonian, which is in here somewhere, is more difficult to spot. There's no obvious break in the rock record. The Cambrian strata are horizontal, and the Devonian strata are horizontal. We have to spot that unconformity by looking at the trademarks of the rocks which belong to the geological periods, by looking at the fossils in the strata. If a geologist were to climb up the Grand Canyon, he'd find, after he'd gone through Cambrian strata, that he didn't find any Ordovician and he didn't find any Silurian fossils. We use that means of detecting unconformities throughout the rock record. And the kinds of fossils we use are graptolites in the Ordovician and trilobites, and also fossils that we call ammonites. There are others as well, but they're three representatives of important groups. And every time we find an unconformity, we know that that represents a gap in the rock record of an area, a time at which the area was laid bare to the effect of wind and water, was laid bare as a land surface. There is an example of an unconformity, an example of several unconformities, in fact, in Ontario. And if you look at the geological rock record of Ontario, one can spot a similar kind of picture to that in the Grand Canyon. Like the Grand Canyon, the oldest rocks in Ontario, forming the basement for everything else, are metamorphic rocks, which were subjected to great heat and pressure in the roots of a mountain belt. These are north of Sudbury. After the mountain belt was eroded away, the land surface sank beneath sea level, and these sedimentary rocks were deposited on the old land surface, creating, therefore, an unconformity. These sedimentary rocks were in turn raised above sea level and eroded to form a land surface, and on that land surface, the limestones of the Niagara Peninsula and the Niagara Escarpment were deposited. They form the flat sheet on the horizon. The situation that you've just seen there on film can be depicted in this Pleistocene model. The lower layer here, or wedge, represents the earliest Cambrian strata found in Ontario, exposed over wide areas north of Sudbury, for example. This is very, very old rock, about 2,500 million years old. On top of it is this wedge, which represents the Gauganda. That was deposited as sediment over the land surface, which is now represented by this break. This is then an unconformity between oldest Precambrian rocks and somewhat younger Precambrian rocks. Now, the top of the rock record in Ontario is represented by limestones which are horizontal, and on this model are the green Pleistocene. They're the Niagara Escarpment rocks that you saw in the film. Now, erosion is eating away at that top layer, and the actual position that we see today on Manitoulin Island that you saw in the film is rather like this. This is the Niagara Escarpment, the steep cliff at the edge of those Ordovician limestones, and there is the rather flat area of Precambrian sedimentary rocks, which is exposed over large areas to the north and to the west of Sudbury, for example. And eventually that whole cap of Ordovician rocks will be removed and Ontario will one day consist of bedrock only of Precambrian age, but that's a long way off yet. It's interesting to know that in fact the boundaries between the geological periods themselves are the result of unconformities. Unconformities in Europe, because the geological timescale was devised in Europe. You may recognize some of the names. Devonian from Devon, for example. And they are areas where certain rocks are well exposed and well visible. And the breaks between the systems are breaks between the rocks exposed in certain areas. If the geological timescale had been devised in North America, then the breaks would not have been where they are in Europe. And one of the important tasks of the geologist is to correlate rocks, to match rocks from place to place, from continent to continent, using fossils, in the same way as the prehistorian would match the deposits of one cave with those of another cave by looking at the artifacts that he found in the rubble of the cave floor. That then is the beginning of the way that we interpret the rock record and the way that we use the vocabulary of geology in order to describe the rocks that we discover. The rocks in the Grand Canyon, for example, are not, I hope, to your eyes now just cliffs of white limestone or slopes of red shale. They are strata which belong to geological periods and bear evidence to the passage of time and contain in them fossils which are the record of the development and the history of life. In the next units, we shall be looking at the materials of geology, at the origin of minerals, and at the origin of rocks. And in just about a month, you might be able to call yourself a geologist. I think that you know